The story that I'm going to tell you today is going to go so much farther than you think it will when you see where I'm going to begin. So I'm going to ask you to bear with me for a little bit here. If this initial part seems like it's a little too easy for you or anything like that, feel free to skip some parts, but don't go away because I promise you this is going to be interesting. Because I'm going to start right here from the very simple fact that the zeros of a quadratic function are given by the quadratic formula, which is a fact that, of course, you know. I would just like to point out that if you split up that fraction like this, you get this initial term, which is minus b over 2a, which you should also recognize as the axis of symmetry of this quadratic function. And that makes perfect sense because the axis of symmetry is around where things are symmetric. So both of the zeros should start from the axis of symmetry and go that plus something or that minus the same something to be symmetric. And the something that's being added or subtracted from the axis of symmetry happens to be this term right here. I'm making this comment because I'm going to come back to it later in the video. But for now, if you want to see why the quadratic formula is exactly the way that it is, I do have another video showing it, and I'm linking it in the description. Okay, so the other simple topic that I want to remind you of before we can begin talking about interesting things is inverse functions. So how does an inverse function work? I'm going to do the inverse function of this one that is on my picture right now. Of course, this is not a quadratic function, but in order to sketch the inverse of a function whose graph you already have, what you have to do is to look at the line y equals x, which I'm putting here in gray in the picture. And then what you're going to want to draw is the reflection of the red graph over this y equals x line. Because when you have the graph of the f of x function, they are points of the form xy. Obviously, the x coordinate is horizontal and the y coordinate is vertical. But the points in the red graph are points whose coordinates x and y obey this relationship here, y equals f of x. And the meaning of an inverse function is a function which we call this unfortunate notation, such that it's the opposite. X is the function of y. So graphically, what that means is that the inverse function switches the role of x and y. So where x was horizontal, it's going to become vertical because it is now the dependent variable of this new function that we're making. And the y variable is going to become horizontal because it is now the independent variable. Of course, we're not going to draw it like that because if we did, it would be just the same picture again. But when we sketch the graph of the inverse function, what we do is we switch the names of the variables so that the independent variable is still called x like it usually is. So it's still here horizontally. Every point x, y in the red graph is going to have a corresponding point yx in the green graph. So for example, this y-intercept here is going to become an x-intercept here. And this x-intercept here is going to become a y-intercept here. Also interesting points are the points where the graph of f of x crosses the y equals x line, because on those points, if you switch y and x, nothing happens because they are the same number. They are in the line y equals x. So those points actually belong to both graphs. The green graph is going to be going through here as well. And for all other points, I just want to do this visually, really as drawing a reflection. Graphically, I think that this is easier when the function is closer to the y equals x line. So I tend to start here because this bit is easier to draw. And then I just go from there. And also here is kind of easy because it's the point where they are both together. So now I have to reach the other point. And then from this point, I have to connect to the other point. But now I'm going to be a little bit careful because in order to get to this point to that point, I can't just go in whichever way I want, right? I have to make it look like a reflection of the red graph, getting closer to the line where the red one also gets closer, and then here you see that it gets a little bit farther away. So I am also going to go a little bit farther away, just trying to make it look like a reflection. There you go. That's an exercise that I really like, graphically sketching the inverse of a function. It's interesting that you don't need to have an expression for f of x in order to do this exercise. Like f of x is equal to the square root of x plus x to the power of 3. You don't need anything like that. You just need a sketch, and then you put a diagonal line over there, and then you make another sketch. Also worth noting at this point is that not every function f of x that I could have put here in the exercise would have an inverse function. In other words, not every function is invertible. An invertible function is one that has an inverse function. And the thing is that when you draw the reflection, the green thing that I drew here still wants to be a function, and in order for a graph to be a function, it needs to pass the vertical line test. And this one does. Every vertical line that I put here in the graph, you see it's only crossing my green function once. Was this luck, or did I know what to do with my original red function in order for this to be an okay example? Well, the thing is that, like I mentioned, the inverse function is switching x and y. So everything that was x becomes y and vice versa. And there are some consequences of that switching of x and y. For example, we've already mentioned in the previous example that a y-intercept is going to become an x-intercept and vice versa. That's kind of obvious because I'm switching x and y, so literally the x-intercept becomes the y-intercept. But other things can be less obvious. For example, if I start with an exponential function here, this is my f of x, and now I'm going to sketch the inverse function to that. So I need my y equals x line here to reflect over, and I'm going to switch the y-intercept with an x-intercept. I'm going to get closer to the line here as the red one does, and then I'm going to go farther away again over there like I was talking about in the previous example. But I am switching everything x for everything y. So x is horizontal and y is vertical, which means that I am switching everything horizontal for everything vertical, and vice versa. But this red function here has a horizontal asymptote, which means that the blue one is going to have a vertical asymptote, which I am putting right here. The equation of the horizontal asymptote of the red one was y equals 0. And so I am switching x and y, right? So the equation of the vertical asymptote of the blue function is x equals 0. Of course, if you already know that I am talking about exponential function here, of course, this is a logarithmic function down in the other one. That's where the vertical asymptote for the logarithmic functions comes from. It's from the fact that it's the inverse function of something that has a horizontal asymptote. But another interesting thing that also switches x and y in not as immediately obvious a way is that when you talk about the domain of a function, that is all the possible values of x. And when you talk about the range of a function, that is all the possible values of y. So domain and range also has to be switched when you're doing inverse functions, which is why the domain of an exponential function is all real numbers, and the range of the logarithmic function is all real numbers, but the range of the exponential function is only the positive numbers, which means that the domain of the logarithmic function is just the positive numbers. That's where that comes from as well. Okay, so I'm not going to talk a lot about exponential functions and logarithmic functions in this video. I do have another video that is all about exponential functions. I'm going to link that in the description as well. But what we were talking about here is the fact that in order for the red function to be invertible, then its inverse function, the blue function, needs to pass the vertical line test. And this one does pass the vertical line test because every purple vertical line that I am putting here is only crossing the blue function once. But the way that I could have seen already in the red function that that was going to work is by looking at horizontal lines, because look, I am switching everything horizontal with everything vertical. So if my blue function is going to pass the vertical line test, then I need my original red function to pass a horizontal line test. And the exponential function certainly does pass that test, as does my previous example. Look, my red function here also passes a horizontal line test, which means that once I reflect it over the y equals x line, the new function, the green one, will pass the vertical line test. So it is a function. So it is the inverse function of the red one, and the red one is invertible. Now, the only way for a function to not pass the horizontal line test, and therefore to not be an invertible function, is if once it crosses a particular horizontal line, it comes back down and crosses it again. This doesn't stop the function itself from being a function, because it is still passing vertical line test here as it goes up and down, but because it went up and down, it's crossing the horizontal line multiple times. So if I try to invert that, then I would get a green function that is going to the left and to the right, something like this. Look, this is not a function. This doesn't pass the vertical line test because the red one did not pass the horizontal line test. So the moral of the story is, in order for a function to be invertible, it can't have any local minimum or local maximum, because when you reflect that, it would make something that goes to the left and to the right, and a function cannot do that. Now, what is the simplest kind of function that you can think of that has a turning point? It is a quadratic function, of course, that has this turning point right here, which is the vertex of the quadratic function. So we are going to go back to talking about quadratic functions pretty soon. But first, I want to tell you about the other type of inverse function exercise that I really like, which is to invert a function algebraically. I am a very big fan of graphical exercises in a variety of contexts, including this one that I've just showed you. I really like inverting functions graphically, but I also like to do this one algebraically as well. So here is a particularly complicated looking example. Let's just go through the steps of how you invert a function algebraically. Hopefully you will see that there's nothing exactly complicated about this example. It just looks funny. But the thing is that you begin such a thing by remembering that the points in the graph of this function are the points x and y, such that y equals f of x, right? So we can take away this f of x here and just put y equals that. And then the second thing that you're going to remember is that when you want to invert a function, you have to switch the roles of x and y. So this y here is going to become an x, and that x is going to become a y. Of course, if we had multiple occurrences of the letter x in the expression of this function, you would have to change all of them to the letter y. But because in my example I only had one, so I just did it once. And by the way, the fact that there was only one is the reason why I say that this example is not particularly difficult, okay? Because everything that you need to do now is to isolate y in this equation here. So you're going to do that by just doing inverse operations, a bunch of them in the correct order as needed here until y is isolated. And I do have a whole other video talking about that kind of exercise. But for here, let's just do it, right? So we'll begin by subtracting 2 on both sides. And now we are going to put both sides of this equation to the power of 3. I am not sure if it would be important at this moment to expand this x minus 2 to the power of 3 here. But just in case you want to do it, just make sure you do it correctly, right? Because it would be a very bad mistake to do this. Ouch, it hurts. That's not how this goes at all. This requires a binomial expansion, right? I also have videos about that. But to the power of 3 means that you put x to the power of 3, then minus, well, it's going to be 6 now because it's 3 times this 2. The next one is 3 times 2, 2. So it's 12 here, x, and minus 8 finally, which is 2 to the power of 3. I don't usually do that though in the kind of inverse function exercise. Okay, I'm just going to leave it like that and now subtract 7 from both sides. Finally divide both sides by 2 and take the fifth root on both sides to get this very beautiful looking answer right here. There is a specific reason why in the beginning I chose odd numbers for both the index of the root and the exponent in there. It's because odd degree power functions look like this. So they pass the horizontal line test, whereas even degree power functions, they look like this, kind of like a quadratic function. So they don't pass the horizontal line test, and therefore I don't like putting them in algebraic inverse function exercises. However, that is exactly what I'm going to do today. I want to talk about the inverse function of functions that are not invertible. So I'm going to start with this quadratic function. Okay? How can we think of inverse functions of this function since it doesn't pass the horizontal line test and is therefore not an invertible function? Well, we can begin by doing the graphical part. And I was a little bit careful when sketching here. My roots are in the correct places, 1 and 3. My y-intercept is also correct, which is 3 here. The vertex, I think, is in the correct point, like 2 and minus 1. I tried, at least. So by coincidence, the y-intercept and one of the x-intercepts are the same. So that's going to stay here. But we do have 2 x-intercepts, so we want to mark 2 y-intercepts right there. The vertex is also an interesting point to mark precisely, which I just said is 2 and minus 1. So let's put it at minus 1 and 2. Now let's attempt to connect the dots in a way that looks at least a little bit good. There we go. I think that's acceptable. And clearly the green thing does not pass the vertical line test. It is not a function. But you know what I'm going to do? I'm just going to paint one part of that function in a different color. I'm going to paint it blue. And now I don't have 2. I have 3 functions in this graph. I have the red function, which is the quadratic. I have the green function and the blue function. So the thing is that the red function isn't invertible if you look at the whole red function, but if you just look at half of it, then that half, if it's adequately chosen, then in that half you don't have the turning point, which is the problem for a function to be invertible. So I'm just going to paint the vertex here, and everything to the right of the vertex I am going to paint orange. And now I have 4 functions. Let's talk about this domain restriction that just happens. The red function is that quadratic for x less than 2. And the orange function has the same expression, but the domain is different. It's x bigger or equal than 2. Actually, I'm going to put the equal on both domains. It doesn't really matter if you have a point that belongs to both domains. They are different functions. So that's the expressions of the red and orange functions. Now I want to do the green and the blue one. Let's try to do this in the algebraic way. So we have y equals x squared minus 4x plus 3. In principle, this works for both of the functions. I'm not going to have to do the same calculation twice because the only difference between the functions is the domain. Their expression is the same, so algebraically it shouldn't matter. But now that I am going to invert algebraically, the next thing that I need to do is to switch this y for an x. And remember, I mentioned in the other example that if you have multiple x's, you have to switch all of them to y's. So that's what I'm going to do. This is a y, and this is also a y. And now the next step is to isolate y in this equation. But comparing this to the previous example, this one's a lot harder because in the previous example, I only had one y, so all that I was doing was inverse operations on both sides of the equation over and over again until it was over. That is not the way that this is going to work here, because I want to isolate y in something that is a quadratic equation for y. So how do we do that? Let's treat it like we do every quadratic equation. The first thing that we do is that we want it to be something, something, something equals 0. We don't want this extra x thing on the other side here, so let's rearrange. And now we are going to use the quadratic formula, of course, because that is how we handle quadratic equations. We just have to be sure we know what a, b, and c are in the formula. Well, a is 1 because there is nothing multiplying the y squared here. B is this negative 4. And c is 3 minus x. So let's plug all of that into the quadratic formula. Let's do that slowly. First of all, a is 1, so it doesn't need to be here and it doesn't need to be there. Now b is negative 4, which means that minus b is just going to be 4. And b squared is going to be 16. The part that people can get confused about is the c, because the c is 3 minus x. So this thing that was reading 4c is now going to read 4 times 3 minus x. For this particular example, because it can look very nice, I think I do want to factor out 4 out of this square root like a 2, so it's going to become this, because now I can cancel and get rid of that denominator. This one's going to disappear, this one's going to become a 2. Now I'm going to distribute this minus here, minus 3 plus x it's going to be, and 4 minus 3 is 1. So that's my final answer. Let me just write it down prettier here. 2 plus or minus the square root of x plus 1. Let's put that closer to the picture that we had. Okay, so what's that? What does that mean? It was an algebraic exercise that we were blindly doing, but now I want to remember what this means for the picture that I was drawing. First of all, something with a plus or minus in the middle can't be the expression of a function, because what is plus or minus? Is it plus or is it minus, right? A function can only have one answer. That's actually the whole point of the vertical line test. But the thing is that, remember, I wasn't trying to do this algebraic exercise in order to come up with one function. I was trying to do it to come up with two functions, which is the blue one and the green one. So what's happening here is that the plus is the blue function and the minus is the green function. Now, how do I know which one is which? Is just because plus goes up and minus goes down. And look, the green function is going down, the blue function is going up. So the blue is the plus and the green is the minus. I'm going to wrap up the exercise here, but first I need to fix this because I just realized that I called both of my functions by the same letter. So there you go. Now it's fixed. One is f and the other one's g. And the blue function, which is the top one, is the inverse of which one of those? Well, the blue is the inverse of the orange. So that is going to be the g inverse function, which is going to be 2 plus the square root of x plus 1. And then the green function, which is the inverse of the red function, that is going to be the f inverse function, which is 2 minus the square root of x plus 1. And notice how in terms of the domain of these inverse functions, it's all making sense as well, because the domain restriction that we have here is that we can't take the square root of a negative number, so we need to have x plus 1 bigger or equal than 0 for the domain of both of the inverse functions. That means that x is bigger or equal than negative 1, which is exactly what we see in the picture up there. The blue and the green functions only need a domain starting at negative 1, because that is the coordinate of the point. That is the reflection of the vertex of the original parabola. And that wraps up this exercise, but it opens the question about other functions that are not invertible, right? And what could we do in order to invert even more complicated functions that don't just have the one turning point? So earlier, when we were doing this example, I mentioned that the odd exponents were good for this kind of exercise because they didn't have turning points. Of course, I was just talking about power functions like x to the power of 3, x to the power of 5. I didn't mean to say that every odd degree polynomial is like that, because of course it's not. This here is my favorite degree 3 polynomial. It is x cubed minus x, and it has this wavy shape. It has three roots, which you can easily check just in your head that they are 0, 1, and -1. Those are the three numbers that make this function equal to 0. It clearly does not pass the horizontal line test, because when you do this, you are crossing the function 1, 2, 3 times. Well, up here you're only crossing it once, but that doesn't matter, right? It already broke somewhere, so it's broken. But if you wanted to split up your function into three parts, three different domains, and invert each function separately, then you can do that. It would be these three functions here. And the place where the domain changes needs to be the turning points. Not sure that I need this right now for the purposes of this exercise, but finding these turning points is an easy calculus exercise. You just do the derivative, which is 3x squared minus 1, and then you set the derivative equal to 0. 3x squared equals 1, which means that x squared is a third, and x is plus or minus the square root of a third. In case a lot of people watching this don't know calculus yet, I am going to try not to use that information as we move forward in the exercise, but I might need it, so I'm just going to leave it here in the picture. And this kind of calculus is not that difficult anyway. I am going to point to another one of my videos where I do this introductory part. But the problem now, if we are trying to handle this problem in an analogous way as we did the parabola one, is that over there we had very easy the quadratic formula, and this is not quadratic. This is a cubic, and a formula for solving a cubic equation is a much more complicated thing than the quadratic formula. But in theory, that is what we want. We have this curve, which is y equals x cubed minus x. We are looking for the inverse of this, so we are going to switch the variables x and y. And this is the equation that we want to solve. It is an example of a more general kind of cubic equation in which you could have all four of the coefficients, a, b, c, and d. But in our example, a is 1, b is 0 because we don't have a term in y squared, c is -1, and d is this minus x here. Now, here's the thing. A formula for this kind of thing exists, but nobody knows this by heart because nobody uses this in practice for anything. So I wanted to include it in the video, so I went to look it up. And this is what the formula looks like. It's in X here and not in Y because that is the way that the formula is usually written when you look it up. So I'm just going to pretend that I had not switched X with Y in the inverse function. These are the coefficients that we had, that we were just talking about. And then when we plug those into the formula, you get this very complicated looking thing. It doesn't look quite as complicated as the original thing on the top of the page here because our b is 0. So all of these terms that have a b, all of them become 0. So we have a lot fewer things in our example. We actually don't have this final one here as well, but it is still a very ugly looking thing. And I know some of you may be wondering right now, where are the other solutions? Because when I used the quadratic formula, there was that plus or minus that gave me the two solutions that I want. And in this case, sometimes I want to have three solutions. For some values of y, I want to have a pink one, a green one, and a yellow one. For other ones, one will be enough, but sometimes I'm going to need three, and this formula is only giving me one value of x. Now, I will talk about this in a little bit, but first I want to say a few more things about just this one that is highlighted in pink right now. I want to mention the domain of this function that we are finding, because just like in the quadratic example, we had a domain that was x bigger or equal than -1, which made perfect sense in the example that we were dealing with. Here, there is probably a domain restriction as well, but it's not because of the cubic roots. Cubic roots don't present any kind of domain restriction because you can take cubic roots of positive numbers are positive, and you can also take cubic roots of negative numbers. Those are just negative. It's just like the cubic root of -8 is -2. But this formula also has square roots in it, and square roots do have the same domain restriction that we just mentioned before, which is that the thing that's inside the square root needs to be bigger or equal than 0. So notice that it is the same square root twice here, so it's not going to be two different restrictions, but we do need y squared over 4 minus 1 over 27 to be bigger or equal than 0. And because the variables are going to be inverted, it's actually not a y here. It's going to be x squared over 4 minus 1 over 27 has to be bigger or equal than 0. This is going to be the domain of this function. So you need to have your x squared bigger or equal than 4 over 27. This is a quadratic inequality that you are trying to solve. So x squared minus 4 over 27 looks like this. And the zeros of this thing are plus or minus the square root of that number. And the values of x that are going to make this quadratic be bigger or equal than 0 are actually these values of x bigger than that root, and these other values of x here, which are smaller than the other root. So in the end, you have a function here, our inverse function. It has a domain that has a hole in the middle. It is okay on the left, then not okay in the middle, and it's okay again in the right, as we see in this picture here. Now, this is where I thought things started to get weird, because this hole in the middle makes sense with what we were just talking about, but I think the hole is a little bit too big, because this point here, which is the one with 1 over the square root of 3 that I was talking about before, that point is actually kind of here in the inverse function. And our other turning point here is reflected down here. So here's why I'm thinking that the hole looks too big, because in this hole, we still need 3 parts of the inverse function. We need one here in the middle. This blue part, when considered alone by itself, it is a function. It passes the vertical line test. And the third inverse function that we need is this purple one down here. So now I want to get back to the fact that I mentioned a while ago that this was just one solution to a cubic equation, and we actually expect the cubic equation to have 3 solutions, just like we expect the quadratic to have 2. But of course, that means that this is just part of the formula. We are missing 2 solutions, and the formula that has all 3 solutions, I couldn't find one that looked in the exact same format as the one we were just looking at, so that's why this one looks a little bit different. The denominators have all been pulled outside of the cubic roots, so this 3a here is 27a cubed in here, or 6a squared in here. It's in there. It is the same formula, but it's just been typed in a slightly different way. Okay, so the over 3a in this version is just in the single term there, and the other ones, he has kept the 3a inside of the cubic roots, where this guy decided to pull all the fractions outside of the roots. I just wanted to point out that it's not a completely different formula. It's the same thing, it's just written in a slightly different way, and we're going to have to deal with that. But the thing that you should actually be noticing here is that this part of the formula looks exactly the same in all 3 solutions, all 3 roots of the equation. And the only difference is that this one is multiplied by this thing, and in the other one, they are the other way around. So notice that this one has a plus, and this one has a plus, this is minus, and this is minus. But this should attract our attentions because these are complex numbers, right? I here is the square root of -1. And maybe you weren't expecting to talk about complex numbers today, but maybe you were, because when we talk about the domain restriction for a square root, that the thing that is inside it needs to be positive, it's exactly because if it's negative, then we are talking about complex numbers. So the thing that I think is happening here, the reason why my software didn't draw any one of the three inverse functions inside of the whole, but I do think that one of them actually exists because the other two are going to come from the other two formulas that we weren't looking at here. But the third one has to be this one. And if I had to guess, I would guess that it's the blue one just because of symmetry. I don't know why it would choose one side or the other. I'm not actually going to do that calculation, okay? It's too much computation by hand. It's not that I don't like algebraic exercises and manipulating things by hand, but everybody has a limit. And this one is like over my limit. I don't want to do this. It's too much calculation by hand. But I think that what is happening is that, well, for the parts of the domain that everything is okay, then it's just okay, right? It's here and there are no square roots of negative numbers in that formula. But I think that for this part of the domain, those two square roots are being square roots of negative numbers. So they are involving complex numbers. But because one of them is coming with a plus and the other one's coming with a minus, I think they're canceling out. I think the complex part of one square root is canceling out the complex part of the other square root, making the whole thing x into a real number. But I don't think that the software that I use to come up with this image is knowing how to handle that. That's why it's not showing anything. So I leave that as an exercise to you if you want to work out all the complex numbers here and see if my hypothesis is correct, that this is actually what's happening and that everything that is complex is going to cancel out. But in the meantime, I do have some more comments to make. First of all, look at that minus b over 3a term that is in all three of the solutions to the cubic equation before we even get into the complicated part with the potentially complex numbers and all the square roots and cubic roots. There is this very simple looking term, which is minus b over 3a, which should be reminding you of the minus b over 2a that we have for the quadratic formula. So in the quadratic formula, you know, because you've memorized it a long time ago, that minus b over 2a is the equation of the axis of symmetry. And I want to look at it as the average value of the roots. So it's adding both roots and dividing by 2. Because if I look at it this way, then I can do the same thing for a cubic. I can think of adding up all three roots, whether they're complex or not, and adding up all three of them and dividing by 3. That would be the average root of the cubic. But this argument by analogy shouldn't be enough. But this is exactly what this is. Minus b over 3a is the average value of the three roots, and I'm going to show you why. If you take your degree 3 polynomial and you put it into factored form, I'm calling x1, x2, x3 the roots of the equation here, just like the formula in the image above is doing, okay? So if you think that it started out in the factored form and then you're going to do all of the distributives, first of all, the term with x cubed is just going to be xxx, which gives us back the ax cubed that we need. But when we want to make the x squared term, then, well, we're always going to need an a. But then sometimes we're going to have x1 xx, which is x1 times x squared. Or maybe we have x x2 x, which is also an x squared, but this time the coefficient is x2. Or we can have x x3. And in all three cases, we are getting a negative sign here. So I'm going to change this plus to a minus. And there is an x squared here, but I'm going to put it a little bit later. So remember, the first time we had an x1 multiplying the x squared, And then the second time we had an x2 multiplying the x squared, and finally we also had the x3. So this is also not new. This is how we deduce the formulas for sum of the roots in a polynomial. If you keep going and you do the last term, you're also going to get the formula for the product of the roots of a polynomial. I don't have a video specifically about that, but it is vaguely related to binomial expansions, right? So I'm going to leave a link to that one in the description as well. But the point is that if you compare the original general form of your polynomial here that had a plus bx squared, and now you have minus a, these things multiplying the x squared. So these two things highlighted in yellow need to be the same. And I'm calling that the sum of the roots, which means that the sum of the roots is minus b over a. And if you want to do the average of the roots, in this case, there are 3 roots. So you're going to take the sum and divide by 3. So you have to divide by 3 on the other side as well. And that is the average of the roots. Now, I am going to stop that there for a minute. I will get back to it. But I need to tell you about something very important, which is called the roots of unity. And this is a complex numbers thing. I am not sure to what extent this is technically something that we should mention in the syllabus of the IB course, but I do like to mention it because it is so important and it comes up a lot. Now, unity, of course, means 1. And root is like a square root, except it doesn't have to be a square root. It can be any index root. And now you're thinking, wow, this is stupid because the square root of 1 is just 1. What else is there to talk about? And in the real numbers, you would be pretty much correct. But the thing is that this is a complex numbers thing. So when I say unity, I mean the number 1, so it's specifically this point here in the complex plane, but I will be interested in looking at the whole unit circle there. In the real numbers, when we say the square root of 4, for example, that's just 2, right? We just mean the positive 1. It's a mistake to say that the square root of 4 is plus or minus 2. That's not the technical meaning of the square root. That's why in the quadratic formula, we have the plus or minus in front of the square root, right? So that you can account for both the plus and the minus. It's not inside of the root itself. So it is a different thing to say that the nth root of y is equal to x, or to ask for the solutions of the equation y equals x to the power of n. And it is a lot more in this sense that we are going to talk about the roots of unity. I am interested in what complex numbers to the power of n are equal to 1. Of course, 1 to the power of n is always going to be equal to 1, no matter the value of the n that you are using. But for example, if n is 2, you already know that there is another one, because negative 1 to the power of 2 is also equal to 1. So for n equals 2, you would have this one as another root of unity. 4 as well, in fact, any even number. But when you do 4, you also have I to the power of 4 is 1, and negative I to the power of 4 is also 1. And you see that when you think of multiplication in complex numbers as rotation, which is a very important way for you to think of multiplication of complex numbers. You have to be thinking of the complex numbers in their polar form, so that when you multiply two numbers, well, the modulus is just going to multiply one by the other, right? So r times s. But the arguments, which in this case are theta and alpha, they are going to add to each other. And when you have a point in the complex plane, which is theta, and you're going to add another alpha to the argument of that complex number, that is a rotation. That is rotating by the angle alpha. So you have to be thinking of that in terms of rotation. And of course, the modulus can change as well if you're multiplying it by s, but that's not important. I want to talk about the angles because all of my examples here are going to have modulus 1. I am in the unit circle. I'm looking for the roots of unity. So this one up here, which is the number I, it has started here and went 90 degrees. So if you put it to the power of 4, it's 90, 90, 90, 90, and it's back where it started. This one here, which is the number -1, is going to be 1, 2, 3, 4. So it went around twice in the unit circle, but it also got back to where it started. And finally, -I is going to do the exact same. You could think about it rotating the other way, but I don't want to do that. I want to think that -I just has this argument, and I'm going to put it to the power of 4. So I need to rotate it another 1, 2, and 3. So it went around even more, but it got back to the same place. So these are the fourth roots of unity. 1 itself, I, -1, and -I. I'm going to do another example with the cubic roots, but they all work exactly the same. So if you are looking for something that to the power of 3 gets back to the same place, it can either be the number 1, which is always going to be one of the roots, and it doesn't go around the circle at all, right? It just stays there. But if your original number z is just 1/3 of the way around the circle, therefore 120 degrees here, then when you take this z to the power of 3, it's going to get back to the number 1, because 1, 2, and 3. So this one here is z squared. And it's also one of the roots of unity, because if you started by going 240 degrees, then another 240, and another 240. You went around the circle twice, but you got back to the same place, so you are also a root of unity. Writing this number in polar form is super convenient. And if you know your trigonometry well, you can also write it in Cartesian form if you want, but I am not really sure why you would do that. And this other root of unity here is with 4 pi over 3, and its coordinates are this. But the moral of the story is that the roots of unity are always equally spaced around a circle. So if you want the 8th roots of unity, you take your circle, you cut it into 8 equal pieces, and those points are going to be the roots of unity. 8 is a particularly easy number to draw, but it could be any number. 5 is very difficult to draw, but I tried it anyway. So here are the 5 roots of unity. These are the numbers that when you put them to the power of 5, the answer is 1. And then if you want to have a number that to the power of 5 is equal to 2 or something else, it's not going to be in the unit circle, but then you just treat the modulus separately. Then the numbers that to the power of 5 are equal to 2 are not these ones that are marked here, which are z, z squared, and so on, but they are going to be the 5th root of 2 times z, and then times z squared and z cubed, and so on, because you treat the modulus separately, and the modulus is just a real number, so the 5th root of 2 is just the 5th root of 2. So I'm not going to talk about numbers outside of the unit circle anymore, because the modulus is very easy to handle in case you need it. But this is also useful to get roots of numbers that are not 1. So maybe what if you want the cubic roots of I, for example. So now you're looking for numbers such that z to the power of 3 is I. Well, there is one in the first quadrant that you can find just by splitting the first quadrant into 3 equal pieces like you usually do. And this is just going to be 30 degrees right here. That is your first number such that z to the power of 3 is I. But now, if you want the other two, you don't need to calculate anything. You just need to rotate this one 120 degrees and then another 120 degrees, because it will be the same picture as we were just drawing for the roots of unity. So 120 plus 30 is 150, which in this case is going to bring me exactly to the other side of the unit circle. And then this one Well, I don't want to call it z squared this time, because it's not the square of the first one, but I'm going to call it w. And then another 120 degrees later, we are coincidentally right here. And this third answer is just negative I, which, if you think about it, yeah, negative I to the power of 3 is equal to I, right? So there you go. Easy way to solve any equation of the form z to the power of n equals some number. Anytime that you want to solve an equation like this, just know that it is very easy. You don't have to calculate anything. This is just one of those bits of knowledge that you bring with you and you apply it, but you don't have to think about it over and over again, because we are already doing the thinking right now. And k here can be any complex number, okay? So first of all, you look at the size of k, you look at the modulus. If it's not 1, then you keep that information for later, because you are going to need to put modulus in your answers as well. But other than that, you just put your number k wherever it is. You look for its argument. You take the argument divided by n, which is the power that you want, right, to find your first answer. And then for the other answers, you just split this circle into n equal parts, and that's it. So this comes up a lot in ways that I sometimes find surprising. This is an example that I like a lot. So look, we have 13 marks here to start this question. This was not the whole question. The whole question was actually, I think, 22 marks. It was really big. It was a question 12 of an exam, which is supposed to be the most difficult one. But look how easy we are going to get these 13 marks. The equation that we want to solve is z minus 1 cubed equals I. So it's almost the same as we were just talking about, something to the power of n equals k, but we have this minus 1 now, which is a little bit different. So I am going to start by letting t equals z minus 1. I'm not using w because he is using w in the question, and I don't want to get mixed up. And I know that t is a weird name for a complex number, but whatever. So what I want to do is to solve t to the power of 3 equals I, which is an equation that I solve immediately. The first answer is e to the I pi over 6, because this is 30 degrees, 60, 90 to get to I. And then I add 120 to that. I get this other solution here, which is e to the I 5 pi over 6, and adding another 120, I get my final solution, which is this one. This I'm just going to call minus I. But these are values of t, and t was z minus 1. So the values of z were t plus 1, which means that I need to take these 3 red points and shift them 1 to the right. So I shifted the whole unit circle here to the right, and I drew it in green. And now I'm going to bring my points here, here, and here. So these 3 blue points are the solutions to my original equation. Z minus 1 to the power of 3 is equal to I. Now that I've done that, let's see what the question wants me to do. AI, verify that 1 plus e to the, oh, you can't really read that. It's e to the I pi over 6. Verify that that is a root of the equation. Well, yeah, that is the first blue point there. That is a root of the equation. Find W2 and W3, expressing them in that form. Okay, so W2 is going to be 1 plus e to the I 5 pi over 6, which is that other point over there. And W3 is going to be the final one down here, which is 1 minus I. And I know which one is which because the question told me that the imaginary part of W2 was bigger than 0, so it's not possible for the bottom one to be W2. Oh, but he doesn't want me to write it as 1 minus I, does he? He wants me to write in this form. Okay, 3 pi over 2, there you go. Now the roots W1, W2, and W3 are represented by the points A, B, and C respectively. Oh, okay. So let's call the points in the diagram as A, B, and C. Plot the points in an argon diagram. Okay, I've already done that. And now find AC, the distance between these 2 points. Well, that is a little bit of geometry, isn't it? The point C has coordinates 1 and -1, and the point A has coordinates 1. Where's the half? The half is the y coordinate, and then so this is 1 plus root 3 over 2. So now I just want to find the distance between these 2 points, and you can use the formula for distance between 2 points. 13 marks in a question 12. We did this in seconds after having just talked about it for an hour. I know, but this hour is preparation. It's study time. It's not exam time. So take the knowledge with you. It is very useful. I just want to maybe point out a couple of more things, like this shifting to the right that we did here because of the -1 was very similar to what was happening here with the minus b over 3a, where we were trying to shift to the average of the roots of the equation. Because the 1 here that we were shifting to the right, the 1 is this point here, which is the average of the roots of the equation. It is in the middle of all 3 points, equally spaced around the circle, so that is the average of the location of the 3 points. So when I was editing the video, I decided to include an extra comment here because it occurred to me that I'm not sure if it's obvious that the point in the center of the circle is actually the average of all the roots of unity around it. And I think it is kind of obvious for even numbers because you can do by pairs. So this pair, this and this, the average between them is clearly the point in the middle, as is the average between these 2 points. And if you were doing the average of a bigger number like 8, you can still think of the opposite pairs, right? The average between this point and that point over there is clearly the midpoint in the middle, which it all ends up being the center of the circle. Maybe it's not so obvious for odd numbers though. So there is a little argument that I can try to use to convince you that the point in the center actually is the average of all the 5 points. And it's also about trying to put them in pairs because this horizontal line is the real numbers and the vertical line is the imaginary part of the complex numbers that we are dealing with. So that number is a real number, which is the number 1. And these two are conjugates of each other. These two on this side are also conjugates of each other. So when you add up all 5 points, at least you know that the imaginary parts are going to cancel out. So maybe that is not enough to say that 0 is the average of all 5 points, but at least it's a real number because the imaginary part of this one is canceling out the imaginary part of this one, and the same from that pair over there. So the average is going to have to be a real number somewhere in this horizontal line here. But now if you rotate yourself a little bit, and instead of looking at a horizontal axis or a vertical axis, you decide to look at this sort of diagonal axis here that is lined up with one of the roots of unity, and it can be any one of them, but I chose this one. So now you can take the other 4 points and put them in pairs across this axis as well. This is no longer about imaginary parts canceling out because the imaginary part is still vertical. But when you think of the midpoint between these 2 points, which is the average of the 2 points, then it is someone in the blue axis, and the midpoint of these 2 is also in the blue axis. This point is also in the blue axis. So when you take the average of everybody, it needs to be a point in the blue axis. But we had already mentioned before in the previous picture that it also needed to be a point in the horizontal axis. And the only point that does both of those things at the same time is 0. So that's how I know that the average of all the points equally spaced around the circle is actually in the middle of the circle. And also I would like to point out that these are not the same thing, okay? This here is trying to solve a more general problem than that one, because it's not just something to the power of 3 is equal blah. This one has also a term in x to the power of 2 and a term in x. So this is a more complicated, more general situation than the roots of unity that we were just talking about. That is simpler, and I think it's useful enough and worth knowing. This here I don't think is worth knowing. But anyway, what is going on here is also very similar to what is going on over there, because this thing that we're multiplying by here, except for the 3a in the bottom, these are the third roots of unity. It's 1 plus root 3 over 2. Well, 1 plus I root 3 over 2, right? So it is this point here, and the other one is minus, so it is this point here. Okay, so they're not actually the roots of 1, they are the roots of minus 1. And you do need to know your trigonometry and your special angles to understand what I'm talking about, okay? I do have another video about knowing those angles, but I am aware that in this one, I am just going through them as if this is obvious knowledge. You do have to know these things very well. But anyway, because this is a more general problem, a more complicated situation, just notice the pattern of the formulas. This is kind of beautiful. Not both of the cubic roots are being multiplied by the same cubic root of -1. It's one of them multiplying one cubic root and the other one multiplying the other one. And then for the third solution, it's the other way around. This one has the minus and this one has the plus. So the thing kind of makes sense. I just think it is too complicated a formula to be useful in practice. I don't recommend trying to memorize this, but I did learn a lot more about it today recording this video than I knew before. So who knows, maybe in the future I will come to think that this is something worth knowing. I don't know it today by heart at all.